What is going on, guys? My name is Carlton. Welcome back to another YouTube tutorial. Here we're going to be talking about spanning tree and the difference between common spanning tree and per VLAN spanning tree. And later we'll discuss why we prefer rapid per VLAN spanning tree, which is PVST plus, over just regular per VLAN spanning tree, which is just PVST. Now, there are some differences between common spanning tree and per VLAN spanning tree. Number one, common spanning tree is an IEEE standard, meaning it's an open standard, meaning any vendor can implement common spanning tree on their hardware. Whereas per VLAN spanning tree is Cisco proprietary, meaning it's only going to be implemented on Cisco switches. So if you have Juniper switches in your network, you will be running common spanning tree. But if you have Cisco switches in your network, then you will be running per VLAN spanning tree. Now, the difference between the two is that when spanning tree goes to build the tree, because that's all it's doing when it's building the topologies, it's building a tree. With common spanning tree is going to build one tree that every VLAN has to use. So looking at our topology here, we have 4 different switches, and you can see we have multiple links connected between our switches. What spanning tree is going to do what he does, he's going to choose one switch in the network to be the root bridge. Every other switch then has to choose the fastest way to get to the root bridge, and other links will be blocked. So at the end of the day, once the tree is built, certain links in the network will be a part of the tree, certain links will not be a part of the tree. So spanning tree does its thing, and this is the tree that he builds. Now, we don't know why spanning tree built this tree. It depends on who the root bridge is and everybody else's cost in order to get to the root. But this is the tree that spanning tree has built. So if we have traffic that's trying to come from switch 2 going to switch 4, switch 2 has to send the traffic up to 1, 1 sends it down to 3, and then 3 is going to send it to 4. So based on this tree, we see that the link between 2 and 3 is not part of the tree, and the link between 1 and 4 is not part of the tree. And this is the tree that every single VLAN must use. The downside of this is that you have links that are never going to get used unless there is a failure. See, the link between 2 and 3 is not part of the tree, and is not going to be part of the tree unless there's another failure somewhere else in the network where that link must then be added to the tree. Just like the link between 1 and 4 is not part of the tree, and it's only going to be part of the tree if there is a failure. So what ends up happening is those links do not get used unless there is a failure, which means they're just sitting there on standby doing nothing for you. It's for this very reason that Cisco decided to implement their own spanning tree protocol, which is per VLAN spanning tree. Now with per VLAN spanning tree, instead of you building one tree, you're going to build a tree for every single VLAN. And all of this is done logically inside of the switch. So I don't want you to think that you have 8 physical switches here. It's still 4 physical switches, but you now have 2 logical trees. So this can be the tree for VLAN 1, and then this can be the tree for VLAN 2. Now, the great thing about having a separate tree for each VLAN is that every tree doesn't have to look the same. So when spanning tree does its thing, the tree for VLAN 1 could look like the tree for VLAN 2, but it doesn't have to. So for example, spanning tree can do what it does and determine this is the tree that he's going to build for VLAN 1. But then he does the same thing for VLAN 2 and he builds this tree. So you're going to see it's certain links that make up the tree for VLAN 1 that don't make up the tree for VLAN 2. But then there's certain links that make up the tree in VLAN 2 that don't make up the tree in VLAN 1. The 2 trees are completely different, and that's fine. They don't have to be the same, and we still have a loop-free topology. So for example, when 2 sends traffic for VLAN 2 to 3, there's no way for it to loop back around because this link between 1 and 2 is not part of the tree in VLAN 2. It's part of the tree in VLAN 1, but not 2. And that's the whole purpose of Per VLAN Spanning-Tree. And what this does is it allows other links in the network to not just sit there dormant, not just sit there not being used. So every link in the network is being used. It's just not being used by every single VLAN. So for example, the link between switch 1 and switch 2 is being used by VLAN 1, but not by 2. But that's fine. At least it's not just sitting there not being used by nobody, like if you were to be running Common Spanning Tree. And if you were to create another VLAN like VLAN 3, VLAN 3 is going to get his own tree. And it may look like the tree VLAN 1 got built. It may look like the tree VLAN 2 got built. It may be completely different. It just depends on how Spanning Tree wants to build the tree for VLAN 3. But the key is every VLAN is going to have its own tree. You're not just going to have one tree that Spanning Tree builds that every VLAN has to use. With Per VLAN Spanning-Tree, every VLAN is going to have its own tree. So now let's discuss the difference between Per VLAN Spanning-Tree and Per VLAN Spanning-Tree Plus. Or why do we prefer to use Per VLAN Spanning-Tree Plus? Because they're both the same, right? You're still going to have a tree for every single VLAN, but we prefer to use Per VLAN Spanning-Tree Plus, which is Rapid Per VLAN Spanning-Tree. And here's why. Ultimately, it comes down to convergence. Convergence is how fast can you detect a failure and switch over to your backup path. In Spanning-Tree's case, how soon can you detect a failure on your root port and switch over to an alternate port? So we have 3 switches here, and we're only going to focus on one tree. We know that PVST, it does a spanning tree or builds a tree for every single VLAN, but let's just focus on one tree to kind of understand how convergence works. So let's just say that for this particular tree, switch 1 is the root. And let's just say that on switch 2, this is a root port and this is an alternate port. So that means that this link is part of the tree, this link is not. So if 2 is trying to go to 3, 2 has to go in this direction. Now, a convergence event happens when your primary path goes down and you have to fail over to an alternate path. So switch 2, his primary path is this way. So a convergence event would happen if that primary path fails and he has to start using a backup path. If the backup path, which is this link right here, were to fail, that's not going to cause any issues or any type of convergence event because he's not using this path no way. It's not part of the tree. But the minute this link or any link that's part of the tree, if this link were to go away, well, now Spanning-Tree has to converge because he has to add another link to the tree. That's when he has to fail over from this link and start using this link and start sending traffic in this direction. Now, how quickly that happens determines how fast Spanning-Tree converges. And there's 2 things you have to take into account. How fast is switch 2 able to detect that a failure has occurred, and how fast is he able to then switch over to his backup port and start sending traffic out of that port. So here's what I mean. Okay, so we know that this is the root port on switch 2, and this is the alternate port. Let's first focus on Per VLAN Spanning-Tree, so legacy Spanning-Tree. When we have a failover event, we have 2 types of failovers. We have a direct failover and an indirect failover. Direct failovers occur when it happens directly on the switch. Indirect failovers are failovers that happen elsewhere in the network. So let's look at a direct failover. A direct failover that causes this path right here to become unavailable is this root port right here going down. So if you log into the Cisco switch, you see that the port is currently up. But let's just say the port goes down. Well, that's a direct failure. And switch 2 is going to know this right away because he's going to know that his port is down and this port can no longer be used. So what he has to do is he has to say, okay, this is no longer my root port. I need to transition this port from alternate, and I need to make him a root port. But here's the thing. Before he can actually start sending traffic over this port has to be in the forwarding state. Now here's what happens if you're running legacy per VLAN spanning tree. Alternate ports are always going to be in the blocking state. Before you can go from blocking to forwarding, is 2 states you have to go through first. You have to go through listening and you have to go through learning. Listening is when the switch is listening for BPDUs on the port. Learning is when the switch is learning MAC addresses on the port. But you can't just go from blocking to forwarding when you're dealing with legacy per VLAN spanning tree. You first have to go from blocking to listening, listening to learning, and learning to forwarding. Then you can start sending traffic this way out of that port. Here's why that is a problem. With legacy spanning tree, we have a timer called the forward delay. By default, it's 15 seconds. What this timer does is says how long does the port have to stay in the listening state and how long does it have to stay in the learning state. So once you determine that you want to take this port from alternate to root, it has to first go from blocking to listening. It has to be there for 15 seconds. It has to go from listening to learning. It has to be there for 15 seconds. Then it can go into the forwarding state. So when you take a look at how long does it take to converge when you have a direct failure, it can take up to 30 seconds. Because when it's a direct failure, like the root port going down, switch 2 automatically knows about this. So it takes him no time to detect the failure has occurred. The problem is going to be when he wants to switch over to his alternate port and start sending traffic. Before he can do that, he has to go through 30 seconds of listening and learning. So when you have a direct failure with legacy spanning tree, the convergence time is 30 seconds because you got 15 seconds of listening, 15 seconds of learning. 30 seconds in computer networking is a very long time. We don't want to wait 30 seconds before our network converges. We want to see our network converging in seconds. So 30 seconds is a very long time. It can be even worse when you have an indirect failure. So an indirect failure would be, for example, your root port staying up. So the port never goes down, but for some reason you stop receiving BPDUs on that particular port. So a BPDU is a bridge protocol data unit. BPDUs contain spanning tree information. That's how the spanning tree topology is built. That's how the tree is maintained, through BPDUs. Now, when you first build the tree, every single switch is going to think he is the root bridge. So it's going to generate its own BPDU and send it out all of its links. When spanning tree does its thing and it builds the final tree, there's only going to be one switch that is the root, and that is the root bridge. With legacy spanning tree, only the root bridge generates and sends BPDUs. So switch 1, if he is elected root, he is going to generate a BPDU and he's going to send it to switch 2 and switch 3. What they're going to do is just update certain fields like the bridge ID inside of the BPDU and just forward it on. But once spanning tree has built the tree, only the root bridge is going to generate and send BPDUs. How often the bridge or the root does this is based on the hello timer, which in spanning tree by default is 20 seconds. So every 20 seconds, switch 1 should be generating a BPDU and sending it to switch 2. The way switch 2 is going to know, and before I say that, let's just say that this is the root port and this is the alternate port. So this link is no longer part of the tree, or it's not part of the tree. The way switch 2 is going to know that his primary path, which is this way, is no longer available is when he missed one BPDU from switch 1. He doesn't get it. right? So the problem with that is that it can take up to 20 seconds before switch 2 even knows there is a problem. Because if he has to miss just one BPDU from switch 1, well, switch 1 is generating these every 20 seconds. So by the time 20 seconds come, I should receive a BPDU from you. And if not, I'm going to think or know something is wrong. So I'm not even going to know that this path is not available for an entire 20 seconds, which is a very long time to be trying to send traffic over a path that's not even available. But switch 2 isn't going to know this for up to 20 seconds. So 20 seconds goes by. He hasn't received the BPDU. Now he's saying, okay, this path is no longer available. You can't be my root port. I'm going to transition you from alternate to root so I can start using this link right here. But remember, before he go into the forwarding state, he has to go through listening, and then he has to go through learning. You got to go through listening for 15 seconds. You got to go through learning for 15 seconds. So the problem with that is it takes you 20 seconds to even detect that something is wrong. Then you got to add 30 seconds on top of that, because the new port has to go from blocking to listening to learning and then forwarding. So you got to add another 30 seconds. So that means that when you have an indirect failure, it can take up to 50 seconds before spanning tree converges to the backup path. 50 seconds is a lifetime in computer networking. That is way too slow. We have to be able to converge way faster than 50 seconds. But that's the problem you run into with legacy spanning tree. 20 seconds to detect the failure, 15 seconds or 30 seconds because you have to go through listening and learning once the other port goes to your root port. For this reason, we do not run legacy spanning tree. We run rapid spanning tree. And here's the difference. So with rapid spanning tree, we mentioned that it's faster to converge than legacy spanning tree. So here's the big difference. So let's just say that the tree has been built. We know that switch 1 is the root. We know that this is the root port on switch 2, and we know that this is an alternate port on switch 2. We know that a direct failure is when the root port, for example, goes down. It's currently in the up status, but now it's in the down status for whatever reason. Switch 2 automatically knows that this path is no longer available. So he detects it right away. So he says, okay, you cannot be my root port no more. I need to make you my root port. So you go from alternate to root. The difference now is that the root port doesn't have to go through listening and learning. With rapid spanning tree, switch 2 can immediately put him into the forwarding state. So he stops sending traffic this way and he immediately starts sending traffic that way. There is no 30 seconds of listening and learning. So the fact that you take away the 30 seconds of listening and learning, when there is a direct failure, the convergence time is 0 seconds. He notices it right away and he fails over to the backup port right away. So you go from 30 seconds with legacy spanning tree to 0 seconds with rapid spanning tree, which is what we like. Now, what about an indirect failure? Remember, indirect failure is when you stop getting BPDUs. Well, here's the deal. With rapid spanning tree, every switch is going to generate its own BPDUs even after the tree has been built. So it's not like regular spanning tree where only the root bridge generates and sends BPDUs. Every switch is going to do this. And instead of doing this every 20 seconds, they're going to do this every 2 seconds. Now, here's how the switches are going to detect that something is a problem. If I miss 3 consecutive BPDUs from you, that lets me know that something is wrong with that particular path. So if I'm switch 2 and this is my root port and this is an alternate port, I should be getting BPDUs from switch 1 every 2 seconds. So if I count to 2, I should be getting the BPDU from you. If I do, I reset my timer. Now, if for some reason I go 6 seconds without getting a BPDU from you, that means I've missed 3 BPDUs, because 2 times 3 is 6. I'm supposed to be getting one every 2 seconds. I haven't gotten one in 6 seconds. That means I've missed 3 BPDUs from you. What that lets me know is that something has happened to where this path is no longer available, because I'm not getting BPDUs from you, which means you are no longer my root port. I now have to transition this port from alternate to root port. And remember, the difference with rapid spanning tree is that there is no listening and learning. So this port instantly goes into the forwarding state, and I start sending traffic in that direction. So with an indirect failure, with rapid spanning tree, the convergence time is about 6 seconds. So 50 seconds with regular spanning tree, 6 seconds with rapid spanning tree. So the convergence time is why we prefer rapid, because with a direct failure, convergence is pretty much 0. And with an indirect failure, it can maybe take up to 6 seconds, which is fine because it's not 50. Right? If you take 50 seconds to converge, that's when your users are going to start complaining that they can't get access to certain parts of the network. But when spanning tree converges in 6 seconds, your users may not even know that something even happened. But convergence is the one reason, the big reason, the main reason why we prefer rapid spanning tree over regular spanning tree. And guys, that is it for this video. I hope you have a better understanding of what common spanning tree is and per VLAN spanning tree. And I hope you have a better idea of why we run rapid spanning tree over just legacy spanning tree. If you like this content, be sure to subscribe to the channel, hit the notification bell. Let's smash that like button so this video can get out to as many people as possible. If you guys have any questions, feel free to leave them in the comment section. Hit me up on Instagram. I'll leave my handle in the description. If you guys want to see me talk about any other topics other than the spanning tree, just let me know and I got you. That's what I do for my subscribers, man. I look out for y'all. So thank you guys again for watching, and I'll see you guys next time.